Hello everyone, sorry I can't be there in person to give this presentation, so I thought I'd record the presentation and it can be played to you. If you have any questions at the end of this particular panel, I'm more than happy to take an email or through LinkedIn and you can ask any questions, but I thought I'd like to give you an Australian perspective on cross-laminated timber in a highly automated plant. We use a very different species in Australia and I'd like to walk you through that now. But before we begin, let's have a look at what mass timber really is and where the sort of genesis came from. Mass timber's commercial origins did come from Europe and it has been used extensively in Europe. But the earliest patent we've got is 1923 for this product called composite laminated timber or composite lumber, and it essentially is cross-laminated timber using smaller board pieces and compression systems to be able to try and improve a composite of timber to make it have a higher capacity for two-way action, so that's the transverse and the longitudinal lamellas, and that then gives it its dimensional properties which are greater than a single board can give in say one orientation. And so this patent is really the first semblance of mass timber, I guess, from Tacoma in Washington State in the US. But more importantly, now we define mass timber as being something more of a commercial element and part of the superstructure. And so mass timber really does replace wet pour concrete or reinforced concrete systems and really forms the new age renewable technology superstructure. And as you can see in this model here, the remainder of the building, whether it be the concrete screed on top of the CLT floor systems or the plasterboard ceilings that have a plenum area and have they look to have some sort of post-tension beam system running through them, and timber columns, this is representative of what mass timber looks like in modern technology. And it's important to remember it's not just the material type, it's also the process. The process of prefabrication is what gives mass timber its competitive cost advantage and time and speed advantage edge. In terms of the material, its lightweight, its stiffness and its strength capacity differential based on the dimensional depth of the material is another reason why you would use it, and it's lightweight. It's a quarter of the weight of 20% of the weight of concrete. Let's have a look at the global expansion of mass timber construction, because I think it's always important to see where we've come from. Back in 2011, this was sort of the landscape. There was a little bit going on around the world, but 2011 was quite an important year because this was the year that Lend-Lease took the technology out of Europe, specifically out of the UK, and the Stora Enso effectively provided the material for the first building in Australia, which is the Forte building, which is a 10-story, 1,000 cubic metre building. And we had a plant set up in New Zealand as well, in a place called Nelson, through XLAM in Australia and New Zealand. And so 2011 really started the genesis of the journey for a commercial way of viewing mass timber. And since that time, what we've seen is the expansive growth all the way through to 2023. And now there is a significant portion of people who are using mass timber construction, and there's a number of plants coming online. There's 2 plants in Australia right now, and there's just a growing movement happening in the US and Europe and around Asia Pacific, and obviously in your area where you're trying to secure enough information and intelligence to support efforts in your country. So how is it made? Well, let's have a look at a short video and see exactly how it's made. This is a video of the XLAM factory, and I'm going to narrate or talk over the top for you. So this is the XLAM fully automated press, and what you'll actually see is the boards coming in. They're laid up on this like a deck to be able to allow the boards to get sorted into individual items, and they get tested for moisture control. So we want to make sure that we have the right moisture content in the boards to be able to allow them to go through the process without an issue. This is finger jointing one end of the boards so that we can actually create a continuous length, and the ContraZinc here not only feeds the boards in continuously, it runs a finger joint through, and in a moment you'll see the glue being applied to the end of the finger joints right here, and that means that we're actually able to join continuously all the boards. They come down and then they get pressed together. The ContraZinc brings the two boards together and makes sure that they are joined in one continuous run. The flying saw here, the red saw you're about to see, cuts the boards to the length that's required, and they run down this conveyor system into a multi-level conveying system, which actually allows the glue within those finger joint systems to dry. And here you can see the boards all being sorted out. Some will become long boards for the length of the billet, and some will become the cross boards, which is for the transverse lamella. It goes through the system until it has enough curing time for that glue, and then it will actually go into a planing and a almost like a finishing type room to make sure that the dimensional depth and width is appropriate for the type of billet. So any variability in the boards effectively gets planed out and they get machined down to the right size. Once they're machined, they get cut into lengths that are required for both that longitudinal and transverse. Here you can see the short boards, so these are the cross boards that are being loaded onto a conveyor system in an array so that they can get picked up by a vacuum lifter and put down onto the pressing bed, which is where they will be glued together before they end up in their final resting place in the press. The boards are now traversing along. The cross boards come down onto the bed, and you can see that happening here. These will go on top of longitudinal boards which already exist on the plastic tray. As you can see now, we've got the first set of boards being picked up. The white centerpiece is actually the bed that they will be laid down on. And these vacuum lifters are very good at placing these boards on in a good way. The whole table now will move so that the glue can be put on it. Now the next layer comes on and it goes on top of it. And you're always going to have odd numbers of layers. Now it'll go back through the glue machine, which is where those purple lights are. You can see it here, the glue being applied. And there's two boards on there, and they're two different thicknesses. And at the moment, the short boards are on the outside. So that tells me that this is a column orientation for this particular panel, not a floor plate. They then go into the press, and the press creates the pressure that's required to be able to make sure the panel stays together. And here comes the panel out of the press. So it's had its curing time. It cures outside the press, and it also cures under pressure in the press. And you can see the glue has foamed up now. That's because it's reacting with the moisture in the timber. So the moisture in the timber is required to be able to work efficiently to make the glue set off. Here again, it goes into the press. This is the next billet, and it will now compress down and ensure that the whole billet comes out. And that's the end of the video for this particular bit. Let's have a look at what it's like to have detailed design around those panels that you just saw being made. Now, the first part is a digital design. To take that product that we've just produced into ordinary panels, we need to make sure we arrange them in the right way. You can arrange them through a number of different perspectives. So the first one is that you can use Revit to do a architectural space and place model. But more often than not, Bluebool or Tekla are the next elements for the engineering analysis to make sure that we've got all of the right engineering properties for the building structure itself, for to avoid catastrophic failure, to ensure diaphragm, to ensure we've got load transfers, etc. And all of that's done in Global. We have this interoperability aspect where we can take what's called an IFC and change it from one program and put it into another program. And here you can see that there's deformation stresses being put on the building, and so the red is a higher level and the light green is a lower level. And the software is able to be interoperable, so we can take it from Revit Autodesk straight into Global and then back into Revit Autodesk. And so to give you a practical example of how this comes together, we're going to look at this particular model. And this model here is of a building. I'd like to say thank you to Franco Piva because he's given me this model to use in this video. And I'm going to walk you through what the model looks like when we do a fly through. And as you can see now, we're going through the building, looking at all the individual elements. And now we've come out the other side and we've transformed the digital version into an actual building. And if we take those same fly-throughs with this particular building, you can see that where we had a digital technology telling us where to place the panels, those panels have now ended up on site, and that building is coming together in almost an identical way to what it was in its digital space. And you can see the final building before the cladding and the aligning goes on. And here you can see the final building with the cladding going on and the windows going in. And if we look at them side by side, you can see that the building looks remarkably like the digital model that we had prior to that. So it's really important to know these digital models really are the genesis for where the technology is placed when it comes to understanding how mass timber buildings come together. And so mass timber systems can get used in very different types of buildings. And one of the buildings is in Spokane in Washington State in the US. And it's the Catalyst building, which was actually done by Katerra before Katerra unfortunately left the planet. The Catalyst building has a Revit model here. Again, we start with that Revit model to see exactly where the place and space for all the panels will go. And then we work into more sort of detailed orientations for each of the panels that we produced. As you saw in the factory at XLAM, each of those panels has a location in a digital model. That digital model then allows us to make the panels appropriate for the type of floor system or the type of wall structure system or column system. Once we have that detailed design, we can actually then do a what's called a shop drawing list. The shop drawing list lists all the panels that we need to make, and this is what's sent to the factory to produce those different types of panels that you saw being produced in the video. And we make each one of those and we put them together in digital space. And here's that digital space. This is the column and beam structure in the green and the yellow at the top. And then we have what's called the intermediaries, which is this orangey red that's sitting in here. And so that model gives us the structural skeleton of the building, which we can then go and lay the panels onto. Now, the panels might be CLT panels, or they might be a hybrid cassette system. And the columns may be steel, but they may be a higher grade glue laminated timber technology. And in most of these buildings, and in particular this particular building, the green beams are actually GLT beams, glue laminated technology beams. Once we have the whole superstructure together, you can see these purple panels. These are the facade. So this is a modular facade system which chased up the building, which means that when the building levels went up, so did the modular system. And all of that's produced in a factory. In fact, this is the factory that produced the Catalyst building. And as you can see on the bottom there, that factory looks remarkably similar, except for it's a hell of a lot larger than the one at XLAM that I was involved in. Once they have the panels already sorted out and ready for production, you then need to work out how you're going to transport these panels. And one of the ways we do that is to break the building down into zones. Once we break the building down into zones and we know which panels go into which zones, we can load trucks up to be able to deliver them so that when they get installed, they go in the right sequence. And as you can see here, I mentioned before that there was glue laminated beams. Well, this also has a CLT lift core. These stair cores in the center of the catalyst building are also CLT. Generally, you find that that's often concrete because regulations in locations like the US and Australia and Europe often don't allow that to happen unless there's a really good fire suppressing system and a building regulatory certifier that's comfortable with having CLT or mass timber cores. It's an impressive building. And here's some under construction shots. And you may have seen these types of shots around. There's a lot of these photographs that are around looking at this building because it has these massive beams and these intermediary ribs and wonderful columns, and the entire building just looks amazing. Again, some more great shots with the facade system, and you'll see the facade system's actually CLT as well. And some more in construction shots from a distance. And so that's the catalyst building, and the world's largest volume of CLT in a horizontal building belongs to the NTU project in Singapore. And this is a Stora Enso project and VHAG, and the building has just opened recently, and there's only been a few photos that have come out. So I've got the original modeling photos, and so the massing project shows this pretty massive curved building. It's in the south sort of business area of the university, and it is an impressive site. This is the wooden model that was produced to be able to verify the location and the placing of the building, and another angle is given here. Again, the systems are very large. They're these very large connection systems with amazing glulam beams and these hidden connections like Pitzel connections. And so Sugaru Ban, who was the gentleman who worked on the design with this, had this very concealed fixing systems, and these were the size of those systems that went into the NTU. And as you can see in the catalyst building, they've used something very similar. This is using material that is in the Katera building that you saw previously, but it follows a very similar, unique design in the NTU building, and this is from the MTU building. So this building is now open, so if you do get a chance to go to Singapore and do get a chance to go and have a look at the NTU building, you will not be disappointed at all. It's an impressive building. So that's my quick run through in sort of 20 minutes of the mass timber production, all the way from how we get the boards to be put through the machines to be able to then go into a press, and then how that panel is then situated in a digital technology, and then how that is configured to go to site. So I've actually given you from the board or the tree all the way through to the completed project in a very, very short walkthrough. If you want to keep in contact with me, you can jump on LinkedIn, and I also have the Mass Timber Construction Journal. This is a two-faceted journal. The first one is an academic journal, so we publish papers that are on science of mass timber and exclusively mass timber. And the second part is we have, through LinkedIn, we report every project that gets published around the world. I do a podcast every week, and I've been doing this for almost 3 years now, and I promote what's happening around the world in mass timber land each week. And also on top of that, We do the social media feed, which is through LinkedIn, and it's all the news articles that we do report on the podcast. The podcast also has special guests coming on. So the special guest just recently is Amanda Sturgeon, who was ex-Living Future Institute. She's now at a company or an organisation called Build by Nature, and that organisation issues grants and does philanthropic work to be able to try and promote mass timber construction around the world. So if you do feel inclined, please come and get in touch with me about the Mass Timber Construction podcast. If you're interested in any media, we have a prospectus that's available at the same time. And if you want to get in touch with me, that's my email address, and they're my associations. And I just want to say thank you so much for allowing me to present today.